right. Before we start, Hutch, are you there?
Yes, I'm here.
Could you pray, please?
Sure.
Thanks.
Dear Lord, thank you for bringing us here. Thank you for giving us the opportunity to learn even though we're not at school. I pray that you stay with each and every one of us, keep us safe, keep us well from the virus, and help us to enjoy time with family while we get the chance, Lord, and help us to seek out your word when doing so. In God's name we pray. Amen.
Amen. Amen. Thank you. All right. So far we talked about electrophilic aromatic substitution, which means when you have a ring, the ring is naturally electron rich. Okay, so it's a nucleophile. And so it invites electrophiles to come over, right? So the nucleophile invites electrophiles. So that's why we called it the electrophilic aromatic substitution. All right. Now, when this takes place, you need to make sure that your nucleophile is electron rich and that nothing in the group will deplete it. Okay. Now, when will nucleophilic aromatic substitution take place? Okay. I think I'm going to ask as many of you to turn on your cameras. Please start your video. I want to see that you are paying attention. I'm sorry, because it looks a little quiet in here for me. There you go. Thank you. All right. So when you have a weakly deactivating group,
can you see me?
I can.
Okay.
Adele, you need to turn off your audio because I hear TV or something. Yeah, thanks. Okay. So when you have a weakly deactivating group, or a very strongly deactivating group, all right, then your ring is electron deficient. Okay, your ring is electron deficient. Now, in this case, okay, in this case, you need a nucleophile. This is already electron deficient, so you cannot send in another electrophile to attack this. So you need a nucleophile. So when you have a ring that now becomes more of an electrophile, you need to send a nucleophile to attack it. Okay. So There are very few reactions that happen this way. These are nucleophilic aromatic substitution reactions. And we'll see what are the requirements for this reaction. Three requirements. Well, first of all, you need to make the ring electron deficient. You need to make the ring electron deficient. And so for that, they should possess a strong electron withdrawing group. Okay, they should have a strong electron withdrawing group. And make the ring electron deficient. Okay. The ring must possess a good leaving group. Okay. So halides, remember, they are good. They are weakly deactivating. And also, they are good leaving groups. So they make the ring electron deficient, and then they're like, okay, when the time comes, they're ready to leave. And the third requirement, the leaving group must be positioned ortho or para to the withdrawing group. So those are the three requirements. And this aromatic compound fulfills all three requirements. And then you have a good nucleophile coming in as well. Okay. And what do you think is the product? NO2. And then, so you get para-nitrophenol as your product, and Br minus is leaving. Okay. Now the question is, what happens if the electron withdrawing group is meta? Remember, your two groups in the ring, the leaving group and the other substituent, they have to be ortho with respect to each other or para. So if it's meta, no matter what the conditions are, it doesn't react. So this has to do with, again, resonance stabilization. Okay, so we're going to look at one of those next. It's a little bit more complex structurally more complex. So you have a Cl group, that's also a good leaving group. And then you have the nitro group, and they've opened up the nitro group. Now your OH minus is going to attack. So it's going to replace the Cl. So what are the resonance structures? Now you have a nucleophile coming in, so it's going to make the ring negatively charged. So can we draw the next structure? Can we follow through? It's going to be a lone pair there. Bond there, bond here. Takes a bit longer to draw this. Okay. Use the skinnier pen. Now from here, you can go two ways.
Shouldn't that oxygen with the single bond be negatively charged?
Yes, yes. You're right. So look at all the charges in there. There are like 3 charges, right? You're right, Shelby. So I can go this way or I can go that way. In the book, if you look in the actual figure for this, they do it a little differently, but I think this is less confusing and more in tune with what you've learned. So there's a negative charge here and a positive charge there. So this can move here, and I'm going to call this pattern A. And what will this do? Because this has an extra bond, this will move out. Let me redraw the structure. Should the nitrogen still have a negative charge? I'm sorry, a positive charge? Yes. Okay. Again, as you draw that, your nitrogen and oxygen, they are adjacent to each other. Not oxygen, nitrogen and this carbon, they are adjacent to each other. Therefore, the nitrogen is able to carry that pair of electrons and bring it outside the ring. So this gives you extra stabilization. That's why they want the I'll use the darker pen. That's why they would like the group to be ortho or para with respect to the leaving group. Otherwise, you will not have this extra stabilization. And then if the, okay, I'll do it slowly so you can follow. And path B, you go on as usual inside the ring. No, I think I did that incorrectly. So this should go here, okay? And this will go and sit on top. This goes here. There's no room there. And also, when you draw resonance structures like this nitro group, when this is not directly involved in the resonance drawing, like here, you don't have to open it up like that. You can just say NO2, okay? I'm going to redraw this so you can see path B. Okay, so that's my plain old structure. Path B. These two are the same, by the way. It looks confusing because we've opened up the nitro group. But like I said, you don't have to open it up here or here. Okay, and then if you do one more, they'll kick the Cl out of the ring. Because it's a good leaving group. Remember, OH is not a good leaving group. I'm going to say that's the product. It's not resonance. Product formation. Got it? Now, you were following along, but if you go to your book, there's a nice clean picture. So look at it. But there are some changes in how they've done, that how they use the nitro group in resonance. They've done it a little differently. I think what I've shown here is more in tune with what we've learned in class. So you may want to redraw it with less confusion and practice. Any questions? But anything that I've missed here? All right, I'll try to draw it more cleanly, give it more room, and then I'll post it, okay? And what actually happens when you have sodium hydroxide? Basic conditions. So in reality, when you have a lot of base in the solution, this is not formed first. Okay, because you have a lot of sodium hydroxide, what the OH minus does is, although even if that is formed, the OH minus will deprotonate. Plus water, okay? So when you use excess sodium hydroxide for the nucleophilic aromatic substitution, you will get the phenoxide ion. Okay, substituted phenoxide ion. So what they do is, this is part one, and then they take the phenoxide out of the solution. And what must they do? They have to use acid, dilute acid, to protonate. Okay. So it's a two-step process. You need to keep this in mind because in the next chapter, we'll be talking about what happens in acidic conditions, what happens in basic conditions. Okay. And this is also why, if you remember, with the aniline, if you use an acid, the nitrogen group gets protonated. NH3 plus. And of course, if you have a Cl or something, so here, the NH2 is an activating group, and so it is OP directing. When you add acid to the solution, you get the anilinium ion. This group, because it has a positive charge on the nitrogen, is deactivating. And it's now meta-directing. So you're able to change the directing power of the group. And now if you want to get your NH2 back, what must you do? Use a base. The base will abstract the H plus and will give you back the aniline. Okay, so these are some of the tricks that you'd have to use when you do synthesis problems. Do you have any questions about the homework that was given to you? Have you all started working on it? You started working somewhat? Okay, pay attention and make sure you understand the process and learn from it. Okay. Now I'm going to quickly talk about this reaction. There are lot of details that I'm not going over. I'm just going to go over stuff that I think you should know. Now here, the nucleophilic aromatic substitution will not occur. Why? Because you do not have another deactivating group here. Okay. So when you try with a weakly deactivating group and a nucleophile, see that? You need an electrophile for doing the electrophilic substitutions. But here you have a nucleophile. So because you do not have a strong deactivating group, no reaction takes place. But what they found later was same conditions, but instead of like 70 degrees or something, they ramped this up. And they found that a reaction took place. And you see here, they use basic conditions on top, and then acidic conditions. Okay. So let's see what the product is after step 1. Phenoxide, okay, step 1. And step 2. Okay. So this is something that you have to keep in mind. And we're not looking at the mechanisms of it. All right. These are called as elimination addition reactions. Now here again, you have a good leaving group. And instead of the OH, let's say you wanted NH2. So these reactions are useful for synthesis. So that's why I introduced those two. Synthesis problems. Okay. So if you have a halogen, usually a halogen, and if you want to make aniline, remember how did you make aniline in the past? There was no direct process. You convert and then you reduce NO2 to NH2. Okay, remember you have to know all your reactions. Now you know another reaction. Make this into a Cl and then use these reagents. Okay, NH2 minus and NH3. And then okay, these are elimination addition, and since we're not looking at the mechanism, you may not understand why it's elimination addition. But like the name says, the Cl group is removed, and then you add on the NH2 group. So it's not substitution, all right? This takes place in 2 steps. If it's substitution, then the NH2 will attach, and then the Cl will go, and the NH2 will be there. That's substitution. Elimination, you remove the Cl first, and then you add on the, you'll actually form a triple bond here, okay? And then you'll add on the NH2. That's why it's elimination addition. You can look in the book for, you know, how the mechanism takes place. It's pretty interesting. So know these 2 reactions for synthesis purposes. Okay, it'll come in handy. How to convert a Cl into an OH group, or how to convert a Cl into an NH2. Okay, this becomes very useful if you remember it. All right. So when do you do electrophilic aromatic substitution? So if you have the benzene ring, and then if you have an electrophile coming in, then you will perform electrophilic aromatic substitution. But if you have a nucleophile coming in, do you have all these 3 criteria satisfied for nucleophilic aromatic substitution? Do you have a good leaving group? Do you have, what's that called? A deactivated ring, and are the leaving group and the other substituent ortho and para. So if those 3 are satisfied, then it'll undergo SNAR is nucleophilic, like SN1, SN2, this is SNAR. And if you don't have that and you still have the nucleophile, then you can have either the 2 products that you can make are something with an OH and something with an NH2. See that? So most of your reactions are going to be that. But then if your ring is highly deactivated, and if you have an OH group as coming in as a nucleophile, then nucleophilic aromatic substitution can take place. But if you do not have a strong deactivating group in the ring, and if you have a good leaving group, then you can have elimination, addition taking place. Here's a list of all the reactions. I think we went over this the other day during lecture, I remember. And this is a summary of the reactions that we saw today. So that finishes chapter 18. And I wanted to start, we have 20 minutes, so I'm going to do nomenclature for 19, unless you have questions for me. Okay, so we're starting off with 19. Any questions so far? I have to keep all my notes intact. Okay. The next chapter aldehydes and ketones. That's what we're going to talk about. And then after that, we'll talk about acids and then amines, okay, a little bit. So aldehyde, you know the difference by now. The aldehyde group, they look similar except that on one side you'll have the H and on the other side for the aldehyde, and then you'll have 2 R's for a ketone. Important in both biology and industry. Simplest aldehydes, this is used as a preservative, remember? You know, formaldehyde, formalin, formaldehyde in water, and then acetone. Okay, use that a lot in the lab as well. What are some well-known ketones and aldehydes? Vanillin, cinnamonaldehyde, spearmint flavor, almond flavor. Benzaldehyde gives you almond flavor, okay? Progesterone and testosterone. So these are cholesterol-like structures. They have the steroid basic structure. So naming, is the usual procedure. For aldehydes, aldehyde, so the ending name is butanal, okay, butanal. And this has to be, this is a terminal functional group. So it's always at the end. And remember, if it's an octane, I mean, if it's a compound like this, you just go from one end to the other and then you figure out where your substituent is. But if you have an aldehyde group, this gets priority. Okay, that gets priority. And this is hexanal. And this becomes a substituent. So aldehyde ends with an AL. Alcohol ends with an OL. So we have these two. Why are they saying this is the correct way of numbering because the aldehyde group, next time I'll bring the priority list. It's on Canvas. So the aldehyde group is given top priority, even compared with OH or the alkene. The only group that's above that is the acid group. Okay. Now, how will you name this? I want you all to name it. And some of you will give me their answer. How will you name that? I'm going to randomly call somebody. So alert, alert, alert. John, do you have a name?
So I actually just got back. My sister needed help with something. I'm sorry.
That's okay. That's okay.
I know we're on naming. Are you just asking us like what to name this?
Yeah, yeah.
Okay.
Take a minute. I'll ask our library 14. Library 14, do you have an answer?
No, I did not. But I'll give a guess. I
Okay.
guess probably gonna be bad, but
Next time, I think I'm gonna have all of you be on video, so I know that you're paying attention. Is that good? That's what some of the classes are doing. And so I'm gonna make that a request, so you're not on your phone, you're paying attention. Okay. KJ, can you give me a name? Give me the ending name.
So it has to end with AL since it has a carbonyl
Yes.
group, right?
Aldehyde group, yeah, very good.
It's
And
going
7?
Yes, 7. So it's gonna be hept.
Heptanal.
Yeah, heptanol, and then it's like
Okay.
a alcohol group.
Mhm.
So it'll be
The alcohol group now, because it's a substituent, you call that hydroxy.
gotcha. Okay.
Hydroxy. Now there's also an alkene. All right.
Mhm.
So heptanol
heptanol.
become heptenol.
Okay.
Heptenal. I know it's not the easiest one. And then at the 5th position,
Methyl.
methyl, and at the 6th position also you have a methyl. So which one should you write first, the methyl or the hydroxy? Hydroxy, right? Okay, 6 hydroxy. And then 5,6 dimethyl. 6-heptenol. Oh my gosh.
Dr. Mary, wouldn't it be 5-hydroxy?
Yeah, you're right. You're right. 5-hydroxy dash 5,6 dimethyl dash 6 heptenol.
Is that a pen or a marker?
Why, it's too thick?
No, I like it.
I know. I had it for years and I rediscovered it. It's pentyl.
Pencil.
Pentyl, you know, the brand name.
Oh, okay.
Sign pen. It says made in Japan. I have had it for a long time, but it's really good. So you can also write it like this, 5-hydroxy. Dimethyl. Dimethyl You can take the 6 inside. I know some of you don't like that. See that? There's no space there and there. So you put the 6 inside. And there's no locator number for the aldehyde because it's always number 1. Because it's a terminal. Okay, so there's no locator number for the aldehyde or the carboxyl group. So not all your naming will be as confusing as that, but it's possible.
Did you say that's always the case?
Hmm?
Did you say that's always the case?
No, it's not always the case.
Okay.
But I think they use this to show the priority of the aldehyde over the alcohol and the alkene. And then, how do you name a ketone? Butane, butanone. Now this one, the carbonyl here, because you have an R group here and an R group on the other side, you have to give a locator number. Look at this one. 1, 2, 3, 4, 5, 6, 7. And here you need a locator number. If it's here, then that becomes an aldehyde. So it's always going to be in between. So this is 3-heptanone, ketone, one. Aldehyde, I don't know why they picked the last one for the ketone and the first 2 letters for the aldehyde, okay? Now, as usual, we will have, you can have stereochemistry, not at that carbon, but at other positions in the ring or the chain. And so this is R2-chloro-3-phenylpropanol, okay? See, there's no locator number for this aldehyde. And this is not a benzene ring, okay? What do you call it when, anybody remember? What's that?
Benzaldehyde.
Benzaldehyde, yes, correct. We don't use this very often, but if you need to, cyclohexane carbaldehyde. So this is cyclohexane carbaldehyde. They made it simple in those days. These are some of the common names from before we had the IUPAC naming.
So I have a question.
Yes.
So for I see that even though like the longest chain is the ring, we don't take it as the longest chain because of the aldehyde. So is it always going to be like that?
Oh, yeah, good question. Okay, so she's asking about this one. So remember we said if the chain outside is longer than 6 carbons, then this becomes a substituent. But here the chain is only 3 carbons and the ring, of course, is 6 carbons. All right. So why is the ring not a parent? That's because this has higher priority and your functional group is outside of the benzene ring. So the benzene ring now, the phenyl ring, becomes a substituent, right? But that is so even if you have an OH group, you know, that's 3 carbons away, or an NH2 group, that's the case. But you're right, okay? But if you had something like this, how will you name this? This would be 1, 2, 3 propyl benzene. Okay. But here you have 3 carbons, but this carries a functional group. So then this gets priority and your ending name is propanol and not benzene.
So that would be whenever you have
A
aldehydes,
function.
or does that count for ketones too?
Yeah, even if you have an OH there, then this becomes a substituent.
Okay, so if there's a functional group outside the ring, it doesn't
Mhm.
matter how long the chain is, it'll
Yes.
always the
Yeah.
phenyl the phenyl group will be a substituent.
Yes. So, but if you have something like this, what is that? This is benzyl alcohol. Okay, so this has a special name. See that? That's part of your naming. But if the OH group is attached to a carbon that's 2 carbons away from the benzene ring, then this becomes the then how will you name this? This will be 4-phenyl 1, 2, 3, 4 butanal, 1-butanal. Got that? Don't think too hard about these things, okay?
Would that just be propanol though? Because the 4 is part of the ring.
1, 2, 3, 4. Yeah, this will be propanol. You're right. This carbon is part of the ring, so it's actually attached here. I'm going to redo this. I'm going to leave it at 3. So this is 3-phenyl 1-propanol. Got that? But if it is attached to this, then this has a special name, benzyl alcohol. All right. Okay. Good questions. So some of these have common names. I think I should finish in a minute. I'll finish up with the slide. The IUPAC name for this has 1 carbon. So what's the IUPAC name? It's an aldehyde, methanal. How do you name the next one then? Two carbons, ethanal. And this, IUPAC name, common name, benzaldehyde. Okay, gives you almond flavor. Common name for this, you use this to preserve your cat and whatever that you use in the biology lab. Formaldehyde, and this is acetaldehyde. And the next 3 slides, that's just a review of whatever you've learned before. And it says what section number I think this section number, I have to reduce it by 1. So this may be 1110. If it is a 3rd edition book, this may be 712. Okay. So this talks about oxidation of primary alcohol. It's a review of what we've learned before. This is a primary alcohol. Predict the product. And then if you have an alkene, what will ozonolysis produce? They will all give you, that's why we're reviewing it here. It will give you an aldehyde or a ketone as a product. So you've already learned about reactions that give you aldehydes and ketones. And then hydroboration. Remember, this gives you you get an enol, and then you get an aldehyde or a ketone. Oxidation of secondary alcohols. This will give you a ketone. See that? These are reactions that you've seen before, so you have to know them. Then if you have an alkene and if you have R's all over, you get 2 ketones. I think it's the last one maybe. And this is a terminal alkyne. This again gives you a ketone. So you'd have to review these reactions. Not necessarily the mechanisms, but the reactions. And this is what you saw recently. Acylation will give you a ketone. And then we'll start section 19.4 next week. All right. This chapter is more mechanisms and reactions. So we'll tackle that next week. So if we finish our quiz early enough, I will come back. I will start 19.4. So we'll see how that goes. All right, any questions? So what's due today? Jamie, can you tell us what's due tonight?
Our theory.
UV theory, right? Yeah.
Yeah, and the packet that we had, and then you moved the sapling to Sunday.
Yeah. So
just
one
those-
sapling on Sunday, and I moved the NMR to Tuesday, I think. Okay. So I'm spreading it out so you don't have too much to do at a time. But
What were you talking about?
Adele, yeah.
No, what she said something about.
Hutch, what is it?
She said something about a packet.
It's the homework for chapter 18.
The sapling?
No, the paper homework. It's on Canvas. Did you not see it?
No.
Okay.
I'll go look at it.
Yeah.
It says chapter 18 and quiz 5. And you click on that and it has a little link for a Word document.
Okay.
Okay. So many of you did the summary. And for the summary, include equations, and just like you do for your theory, for lab, you have to include equations, resonance structures, and I'd like you to hand draw those and then upload the file. Okay, so I'd like you to type it out, and in between, for next time when we do a summary for theory for a lecture. Okay, next time when you do. So, so some pointers for doing a summary, because this chapter has a lot of mechanisms, so you'll be doing some write-ups like that. Okay. So anything else about homework? Do you all know what homework is due when? That's the first thing, because we are getting.
For the quiz Monday, are you just going to like upload it when we take it, and we don't have to print it out? We can just like do it on another sheet of paper.
Yeah, that will be easier. You don't have to. Yeah.
I have not been able to figure out my printer ever since being home. So
Yeah, some others have the same problem. And then will you be able to take a picture and upload it?
yeah, I tried last night on the Post Lab. I did it on a separate sheet of paper, and I
Mhm.
tried to scan it through my phone,
Mm-hmm.
but it wouldn't let me upload the file directly. So
Mm.
I just screenshotted it and uploaded
Yeah.
it as a picture. But I gave Michaela a heads up.
So what y'all can do is, I mean, this is a quiz, so it's going to be like maybe 2 pages or 3 pages at the most, depending on how, how spread out you write. So you can take pictures right away and then email it to me.
Okay.
Okay, so individually you can email it to me. I'll have a link available, but you can email it to me and I don't have to necessarily put it up, unless that way it'll be easy for me to grade and give comments, and I'll put the grades on Canvas. Okay, so if you're not able to upload it, then just scan and send it as an email to me.
And do you know how? I know they sent out an email like a couple weeks ago or something about getting the online version of the textbook if you haven't been able to get back to campus to get your stuff. Do you know?
You
I
don't
can't.
have a textbook at home?
I haven't been able to get to campus ever since before spring break because
Ew.
Hannibal was on like a travel ban and stuff.
So let me find out. Let me see, like if I can send it to you chapter by chapter or something like that. Okay.
Okay.
I'll see, because we are using Wiley, that's our publisher, but we are not using Wiley Plus. We are not using their homework, so they don't have an e-text for you. So I'll see what we can do. Okay.
Okay. Thanks.
And yeah, anybody else not have their textbook at home? So, yeah, I'll find out, Shelby. I think some, like if you, like this is what Tara said, like if you're on campus or, if you're driving by school, she said she could leave the textbooks, available at a certain location. And if you have to tell her what specifically you want from your room and she'll have it available for you. But I'll find out about the e-text for you, okay? Okay. Right. Anything else? So we'll see if I do any more recording on my own, I'll post it. But what I'd like you to do, we are going on to 19, but we are only getting started to get you tested for the first part of 18. So there's a lot of studying to do on your part. So keep up with that, okay? A few more weeks and we can get it done. And lab will go at the pace that I mentioned. So this next week, you will turn in the theory and everything for the ACE alkylation lab. And then you'll also do the post lab for the UV lab. So we'll do little at a time. And the week after, you'll do unknown compounds. So there's no write-up or anything. You'll just do the analysis for the unknown compound. And then the last lab will be the esterification lab. So again, theory, background, I might have a video posted and you'll have to watch the video of how they do the experiment to make the ester. You'll watch it and you'll write the procedure from that or something like that. So with that, we'll finish our lab. The only thing about lab pending would be another quiz, and then we'll have to see how we are giving the final. Okay. All right. Any other questions? Okay. Well, email me and Shelby, I'll find out. And Carly, can you talk to me about taking the test after we finish here?
Oh, yeah.
Okay.
I still need to email them.
Okay, okay. Then I'll send you an email and we'll talk via email, okay?
Okay, that works.
All right, bye, guys. Hope you're still staying safe. Shelby, are you still working?
Yeah, a lot of people are refusing to go in because
Yeah, they
like
don't want
the
to.
pharmacy, there's a lot of sick people, but
Mm,
I'm
Yeah.
still doing it for some reason.
Yeah, just be careful and, but yeah, I mean, um, we commend you for being brave and being there to help people. So,
I'm also getting like a $300 bonus for it, so
okay,
because no
okay.
one else will come in. But
Yeah, yeah.
Are
I
they
know.
hiring?
if you want to drive to Hannibal every day,
She's in Hannibal. Yeah, yeah.
Oh, I'll work there.
Do they provide the mask and everything? Do they provide you with all the gear?
yeah.
Okay, good.
I can't even get a haircut. My barber was for a month.
I know. I think once they open up, all these places are going to be flooded and they'll get more business than ever before.
I hope so.
Yeah. All right. Bye, guys. Have a nice weekend. We'll do the
Bye.
same thing that we always do, stay inside the house. But keep studying. Let's see, I want all A's in this course, right? Well, do your best. That's all. Do your best. All right, guys. Take care.
Bye, Dr. Mary.
Bye. And I'll stop recording. Oh my gosh, I recorded too much. Bye, guys.